Okay, so what I want to talk about tonight is a state machine. And if I need to have a system controlled independently, in other words, I might have an automatic ball lifter that as the driver drives around, it just automatically picks up a ball and puts it in the hopper without the driver having to do anything else other than just guide the robot. That would be a system that I would automate, and I'd use the thing called a state machine in the background to do that. So that's what I want to talk about tonight. And we've kind of alluded to it a couple times. And for me, it's fun just because of the versatility and the power of being able to control the robot with in effect, it's an embedded program. So let's kind of get going on this and talk about state machines. Virtually any vending machine, any microprocessor-based design or system is run by a state machine. And while there's certain qualifications for what that means, it basically doesn't have somebody telling it what to do. It's running autonomously, and that program is embedded in the non-volatile memory of the processor. So in the robot, we use the state machine to perform background functions without the operator having to do anything about it. It also has the ability to utilize sensor inputs and time elements to be able to control its activity. And the neat thing about, at least the way LabVIEW does it, is that we can prototype the state machine itself with a blank VI and then incorporate it in the robot project. So first I want to develop a word description of what's going to happen. So in this case, I'm saying during the driver teleop, we want to execute a precise 90-degree turn when the joystick button is pressed, and we want the turn to be able to rely on data or utilize data from the raw data from the gyro. We always need to have an initiate state, so we zero everything out as far as the controls and the actuators. And in this case, we want, because we're doing this during teleop operations, in other words, the driver is driving, and where you would use something like this, you would, let's say, have a position on the field that was a pre-measured distance. For the setup for the game, they give us all the drawings and all the dimensions on the field and all the features of the field. There could be a line somewhere, there could be a bridge, there could be hardware that's set up, and we know ahead of time by looking at these drawings what the dimensions are and how far that particular point is away from, say, the goal that we want to launch a target at. And so, for instance, the driver may intentionally go up and bump it, knowing that once he's in that position, he can execute a perfect 90-degree turn and be dead on where he wants to shoot the ball. So there's reasons you might do this even under driver control. And the same kind of thing could be done under autonomous, but we're going to be focusing on driver control stuff. So the bottom line is we want the driver to be able to abort it if looking at the system, something goes wrong or somebody gets in the way. And that's just one of the elements that we need to incorporate. So what I've defined are these different states. And first is going to be initialize and the trigger. So each of these columns is important as the way I define my state machines. The state name, the trigger that's going to take me to the next state, what that next state will be, and then what the outputs are while we're in this state. So initialize, we're going to be there for 10 milliseconds, and then we'll advance to the wait state, and where we're in the initiate state, we're going to have the motor 0, and we're going to set the gyro reset to false, so nothing else is going on. Then once it gets to the wait state, it's going to sit there and wait for either the A button or the B button to be pressed. If the B button is pressed, it'll do a right turn, or go to the right turn state, and if the A button is pressed, it goes to the left turn state. And while it's going there, it's going to reset the gyro so we can use the gyro once we start the turn. So if we push the A button, it's going to go down to the left turn state, and the thing that's going to get us out of this state is when the gyro exceeds 89 degrees. And while that's happening, we're going to turn one wheel backwards and one wheel forward, and we know by the polarity on the motors which direction we're turning. So if the right wheel is turning forward and the left wheel is turning backwards, we're executing a left turn. And then once we're there, once we reach that something close to 90 degrees, then we automatically go back to the wait state and we start the whole process all over. So it's a continuous state machine. That's what it's all about. And so we're going to build one in blank VI, and then we're going to incorporate it in the loop B of my robot project. So let's see how I get out of here. I'm going to escape this. Go back to here. Anybody have any questions about what I'm trying to do? My state machine. Okay. So I'll actually draw this in the robot, so you don't have to just watch me wave my hands as we're doing it. So this is already pre-made. The basic features, or the things that identify this as a state machine, I have a while loop that encompasses everything, and then I have a case structure that I've been able to label with the names of each of my states. And in the initiate state, I have an output to the gyro, an output to each of the motors, and then an output to the shift register that tells me what the next state I need to go to is. Now, realistically, I don't need the 10 millisecond delay. And I'll talk more about time as another element that you may want to have precise control over when it comes to a state machine based upon what you're trying to do. And I'll talk about that when we get done. So once we've initiated everything, then we go to the wait state. Once we get to the wait state, nothing happens until a button gets pushed. And so we stay in this mode where every 25 milliseconds it executes another round of the while loop, and it stays in the wait state because that's what the signal that goes out from the previous execution. If button A is pushed, though, then we get a true condition on this case structure, which resets my gyro and then goes to the next state, which is left turn. Once I go to the next time it executes, I go to left turn. And now I'm monitoring the gyro signal with an absolute value, and I want it to get up greater than or equal to 89. And you might say, well, why don't I look for 90? I'm counting on a little bit of inertia to carry it past the point where I give it the stop signal. So it's going to continue in this mode until that signal goes true. So as long as it's less than 89 degrees, I'm going to stay in the left turn mode, or left turn state, and it will continue this operation until that signal goes greater than 89. And at that point, it zeroes the motors. Again, my output to the gyro is false. I go back to the wait state and we start the whole process over. Everybody understand that? You get a feel for what's going on? Leo, do you get this?
Yes.
Do you understand why I'm doing it?
A little bit, yeah, kind of.
So right now, all I'm doing is I want the robot to turn 90 degrees either left or right, and I want the operator to control it with the A or B button. And so rather than him driving the wheels and the motors, the state machine will drive the motor more precisely than you can with your eye, especially when you're sitting across the field from the robot. So that way, if we line up on a feature that the crosshairs on the camera are a known position, and I push the A button, then it does a left turn, and I'm pointed exactly where I want it to point as a result. So let's run this and I'll show you how it works. Now, the other thing that's huge is that because I'm going to make these all part of my robot global data, I can substitute a physical control or a manual control for the gyro, because I can run it before the robot gets built. So let's run it. Now, let's put a probe right here. Now I can see what state I'm in, right? I'm going to stop this and start it again, and you can see, maybe, you can't see it. Let's do this. So I'm going to put this in the execute mode, single step mode, effectively, highlight execution. I'm going to start it, and you'll see how each of these, so first of all, it starts off with initiate, and because my probe is on the output, it never will see initiate. So let's try this again. Okay. Now, I'm going to highlight the execution. We're going to watch this thing step through 2 or 3 loops. So run. It's going to start off in the initiate. That signal comes in here. It goes to wait. And it goes, now because there's fault signals on both of these case structures, it stays in wait. Now if I go push one of these buttons, let's say push button A, here comes the signal around. It sees push button A, up here goes true. It goes to a left turn, it resets the gyro. And now it waits, it stays in left turn until the gyro gets up greater than 89 degrees. So if I take it to 46, you can see it stays, and you can see the value of the motor. The left motor is going reverse, and the right motor is going forward. And when I get up to 90 degrees, it goes one more time through. It sees that this is greater than 89. And then it goes back to the wait state and waits for another button to be pressed. Leo, do you understand that?
Yes.
Okay, and you see what I'm doing up here? I'm using this highlight execution, and I can literally see the signals travel through the logic. And so until I exercise the A button or the B button, it's going to stay in this wait mode, and the motors stay quiet. Okay, so now I want to do this. Now, anybody have any questions on how to do this in a blank VI? Well, I realize I haven't shown you how to do it, so I'm going to show you in the robot project. The tricky part is how to be able to build in an abort override from the driver. So let's talk about that. So okay, so here's the project. Now, I'm just going to quickly talk about the setup. We've already gone through all the different VIs, and I'm going to show you which ones I've already set up. So begin, we've already set up. And if we look at it, I want to see my two motors, my joystick, and if I had a gyro, I would set the gyro up here. I'm acting or pretending I don't have the gyro set up, and I'm going to just replace it with the manual indicator. All right, so that's begin. Everything's closed and finish. So now I'm going to go to teleop. Anybody remember what I do in teleop? Leo, do you remember what we do in teleop? Well, normally in the vanilla version of the robot project, this is where the joystick is connected to the motors. But in the way I deal with it, I disable all this stuff, and I just write in the name of my program to show that I've been to the teleop loop at least once. And I replace it, or I do my motor control in periodic task. So I've zeroed out or disabled everything in teleop, and I want to go into my periodic task and set up my motor controls, and then Okay, now first of all, because I went through my state machine, I know exactly what I need to be on my robot global data. So if I open up robot global data, I know I need to have the x-axis off the joystick, the y-axis off the joystick for teleop, manual control. I need to know I have an A button and a B button. I'm also going to establish a button which enables the state machine. I'm going to call it macro turn, and it'll be what the driver enables the state machine with. And then there's the left turn drive and the right turn drive when we're under the macro itself. And then we're not going to do autonomous, but here's my autonomous controls in robot global data. And this is going to replace the gyro that's not in my robot design yet, just to show that it works. So that's everything in robot global data. All right, in the loop A, now one of the advantages of using this pipe is the fact that if I had other joysticks, I can put them in this pipe just by bundling them. And I think I still may have a video on YouTube. I can put in more motors here. I can put in more joysticks. I can put in any type of other actuator I want to just by hooking it up to these other parts of the pipe. But in this case, I'm staying with what they got. And the advantage is now I just have to pull out of the pipe, in this case the joystick. I separate the values for the axis and the buttons. Now, looking at my driver station, I know button A is the first one off and button B is the second one. And my macro turn is a front-facing button on the left-hand side. And it turns out to be the fifth one down. So I just pick off 1, 2, 3, 4, 5. And I did that by looking at the driver station. And then I want to put and write the joystick buttons and the axis to the dashboard. Now, normally I would have this channel set up to read a gyro that I set up and begin, but because that's not installed on my robot yet, I'm going to use my robot global data for gyro, and that's what we're going to look at when we control our state machine. The second loop B is my drive system. When we're in teleop, basically the operation, the robot mode is teleop, then both of these inputs are false, and my joystick is controlling the arcade drive. But if I am in teleop and I depress the macro turn button, this outside loop goes true, and then my macro drive signals control the tank drive, which is what I'm going to use to turn the robot for my 90-degree plan, my 90-degree exercise. And then when I'm an autonomous enabled, then this inside loop goes true. And at that point, my tank drive is controlled by my auto left and my auto left signals coming from autonomous. Everybody follow that? It's a little bit much.
Sorry, could you show the variables in robot global data again?
Yep. So I know from doing my state machine, and I know I want to do autonomous control. And I can add more to it as I develop my code, but I know in autonomous, I need to have tank drive, so I need an auto left and an auto right. And I put them under a column that's called auto controls. I know for teleop, I need to have a joystick value for the x-axis and a joystick value for the y-axis, because in teleop, I'm going to be an arcade control. And then for my state machine, I want to have a button, A button and a B button to turn left and right. And then I want to have another control that's going to be the enable, state machine enable, that I'm calling macro turn. And then these will be the drives that control it during the state machine. And then this is a virtual gyro that I'm going to test the code with. In other words, until I get a gyro physically mounted, I'm pretending that this is giving me my turn indicator as a robot turns. Did that help?
Sorry, what were the left Mac drive for?
It's this stuff right here.
Oh, okay.
All right, it's going to be controlling the tank drive, and they're coming from the state machine, which I'm going to build right now, right down here. Okay, now how do I do this? Let me get my Okay, what I'm going to do is look at the states right here as I'm designing my state machine. First of all, I want a big while loop. So I'm going to draw a big while loop. I'm going to set it up pretty much like this. Don't ever want it to quit until the program stops. So I'm going to create a constant. I'm going to put a time element. This can run pretty fast because it's not doing that much. So I'm going to set it up to do a 25 millisecond. Now I need a case structure in the center. So the case structure looks like this. I want it to be big enough to contain my logic. I want to set up a enum, which is in the numeric palette. So if I right click, go to the numeric palette, there's an enum right down here. It's blue colored and it says enum on it, and I put it out here. Now this, the enum contains my state names themselves. So it's going to have 4 states: initiate, wait, left turn, right turn. So the way you do that is you right click on it, and I edit items, and I insert the first one as initiate, or INIT. I'm going to do capital just so I know it. Init, then wait, then left turn, and right turn. So this is never going to stop. It'll always be in one of these states. So I'm going to click OK. Now, what's this? This is the secret sauce here. I'm going to take it through with a spool of wire. Whoops. Left click and connect it to the control box on the case structure. Come up to the selector label and right click and say add a case for every value. As I do that, now I come down and now I can see I have exactly what my enum says. I want to come over here to my loop tunnel, right click and replace it with a shift register. So again, it's going to start off with the initiate state, and then it's going to go to whatever state we end up plugging into this shift register on the right-hand side. So this, I go back to my chart, and in the initiate state, I want to set my motors to 0, and then I want to advance to the wait state. Now the 10 millisecond, I'm not going to worry about because the whole overall delay is 25 milliseconds. Now what's going to control the motors in my state machine? While I'm in the state machine process, what's going to control the motors? What was the last question somebody asked me? Do you remember? It's these global variables right here. So I'm going to select one of them. I'm going to change it to read, or write rather. And I'm going to duplicate it. And I like to put right on top. So it's macro left. All right, so what value would the motor controls in initiate? You're right, there's 0. So I'm going to right click and create a constant. I'm going to drag it into the inside. Right click and create a constant. Drag it to the inside. Now the other output that I'm going to have is a thing called, actually there's a couple. One is going to be well, one's going to be gyro reset. And I don't have that yet, so I'm going to put in gyro reset. Gyro reset's going to be a Boolean. And again, the recommendation is to reset the gyro right before you do a measured run or a turn. So once I've done that, so anybody remember what my gyro reset signal needs to be when I'm initiate? Well, it's going to be false. It's always going to be false except right before I do a measured turn. Okay. Now, watch how I do this. I'm going to create a constant over here on this side. I'm going to pull it into here. And now the next state that I want to go to is going to be the wait state, according to my chart. All right, so the next state is always this column right here. So from initiate, I'm going to go to wait, and then from wait, it's going to be determined by whichever button I press. So how do we do that? Let's go to the wait state. Now again, in the wait state, my motors are 0 still, so I'm waiting for a signal. So I'm going to create a constant, create a constant. I've got a nested loop, so I want to use a case structure, create struct. And I always nest inside of false case. We lost Gabe. Now, anybody want to guess what controls the input to these two case structures? Leo, you want to take a shot? What's going to change? What's going to change to take me out of the wait state? Let's look at the chart. What signals will change to take me out of the wait state? So the triggers.
Would it be to set one of them to true?
Yep. One of these buttons is pressed by the operator, all right? And so one of them going true, and so the way you do this, and this is what's being set to true, right? So the way you do this is I'm going to take my robot global data inside, I'm going to change it to read. And it's not going to be gyro reset, it's going to be A button. And then the second one is the B button. Now, when neither one of them is pressed, what state do we want to go to the next round of the while loop? And the answer is, we can look at our chart. If this button, either of these isn't pressed, we stay in the same state. So the next loop has to be again in the wait state. So the way you incorporate that is you just say, okay, I want to stay in the same state. And so visibly I can see until one of these gets pressed, we stay in the wait state. Now when we stay in when the A button goes true, I want my gyro reset to change, because we need to reset the gyro. I want my next state to be left turn. And I'm good to go. So the next one's going to be what happens when the B button is pressed. It goes to true. I'm going to reset my gyro again. So it has to go true. And then the next state is going to be what? It'll be the right turn. Okay, hang in there with me. This will start to make a little more sense as we're trying to move it along. Any questions so far? Right now we've got the wait state and the initiate state. Now let's go to the left turn and see what's going to happen. In the left turn, we're going to execute a turn by moving the motors. And so if we're turning left, then our left wheel is going backwards. What signal do we need on the motor to turn backwards? Positive. And what signal do we need on the right turn to turn left? Negative. Now I'm going to run this on this physical robot, so I'm going to make it a lot slower so it doesn't make it too much noise. So I'm using negative 0.3, but in a real robot, I'd probably use 0.7 or 0.75. Then I'm going to use a select switch. And I'm going to use I want to use the gyro, so I need to remove the reset switch. Now I want to take the value of the gyro and compare it against 89 degrees. So when it's greater than or equal to 89 degrees, I want this thing to stop.
You've still got it as gyro reset.
Yeah, I know, but it's false.
No, I mean the one up there.
Oh,
You
yeah,
just took
yeah.
this little wire thing. Shouldn't that be regular gyro, not gyro reset?
Correct.
Okay.
Thank you. And now I also want to use absolute value because it's going to change polarity. And I know it's going to be going the right direction because I'm using the right motor conditions. Okay, so now my absolute value of the gyro is greater than 89. 89. And it's going to switch. What's the next state that we want to go to? What do we go to when we leave the left turn? When the left turn exits, the next state we go to is wait. And that's why I do the chart, because it keeps you from going batty. So the way this works, I'm going to connect this up here. I'm going to create a constant here. No, I'm not. I'm going to create a constant here. The reason it's acting weird is that I've got it adapt to the source setup. And so the switch was thinking it was a numeric control. And if before it reaches 89 degrees, what state do we want it to be in? Leo, can you guess? We're in the left turn state. We've got the motors running opposite directions, and we haven't reached 89 degrees yet. What state do we want to go to the next round?
Wouldn't it still be wait?
Hey, you got it. I mean, that's the whole thing. It's going to stay in the same loop until it exceeds the value that I've set for it. So then now we're ready to, we're done with this. We're ready to do right turn. It's the same kind of thing, except now we're going to be turning to the right. And so my right wheel needs to go backwards. And my left wheel needs to go forward. And my gyro has already been reset, so I don't want it to do anything. And I'm going to put in my select. And I'm going to bring down my gyro value.
So here's a case where cut and paste would be nice, but you don't like cut and paste, right?
If you're really good, you can cut and paste. But no, I don't like to do cut and paste because of things, yeah, it's just me. So if you get to a point where it's not causing you troubles, then by all means do it. There's another thing. I developed these little quirks to keep me from making mistakes, I've noticed. And one of them is I don't fill in this constant until my last step, and that way it keeps me from running everything by accident. So that's just something I've developed over time. And again, I want this to be absolute value. Okay, anybody have any questions about the methodology? Is it making sense? Now I'll show you. Now these are very simplistic state machine, and you can make them as complicated or as simple as you want. And I'd start with the simple until you got used to the technique. I'll show you one that we did a couple seasons ago that was really complex, and it was really neat how it turned out because they're easy to debug because you can tell what state you're in and where things are going wrong. Okay. So it doesn't like something. What's going on here? This right here. See that white that's not filled in? That's a missing connection. And so I need to, and I get the white arrow. Okay, so that's my state machine, and it's all driven by this enable button that I have on the dashboard. I mean on the driver's joystick. So let's see if it works. I'm going to launch my joystick, my driver station. Let's turn that sucker on. Don't have anything touching anything. Now, one of the things I was kind of loosey-goosey on Tuesday night was I built the robot dashboard, and it gave me what looked like an error. Well, it turns out it wasn't an error. It was just a notification that that file was write protected, and it didn't let me save it. And so what I've done, and I'll just show you what this looks like. Whenever you build something in LabVIEW, in our FRC LabVIEW data, it creates a folder called build. And there's a section right down here. And inside of this dashboard, it sets it up as write protected or read only. So if I change the properties on that, when I build a robot dashboard, it'll save it. And that's what gets executed when I launch the driver station with a LabVIEW dashboard. Steve, that was for you because you asked the question. So now I'm showing default. When I say LabVIEW, it's going to call up that one that I built, and I connected the gyro. I also put in my program name, so I'm writing the program name to the dashboard. Now, if you guys remember, we have robot code because we flashed the RoboRio last Tuesday, and now it's got the same code in it we were playing with that tonight. Now, I don't want to do that. I want to run this new one. So I'm going to overwrite that in RAM. I'm not going to flash it. We're just going to use it to debug it. But what I expect is to see all my controls work. Now this is, to me, this is one of the big advantages of using robot global data as much as I do. We can literally simulate any missing sensor on the robot and be able to debug the code long before they get the robot built. And once that's been confirmed, then it's a matter of just kind of refining some of the variables. I think, Charles, you were talking about compensating for inertia. You'll find that once you get into these 100 pound plus robots, that you can just put braking on the motor controllers and they pretty much stop with not that much inertia. If you don't put braking on it, then it will glide a little bit. Okay, we've got code. We've got a connection to the dashboard. I want to see my robot global data. Now this is what I was talking about. So now before I enable anything, I'm going to be in teleop. I'm going to make sure that all my controls work. So here's my left joystick, and sure enough, it shows on the dashboard both my y-axis and the x-axis. You can see the motors controlling. I can see the joystick values here. I'm going to look at the buttons. So I have gyro reset on the A button, the B button, and then on the opposite side of the board, I've got the C enable. And the way the logic is set up, I have to hold the macro turn down to be able to engage the A turn or the right turn. Now, with that said, I should be able to go in and look at my state machine. Now, periodic tasks started running at the same time I launched it, even though before I've disabled or before I've enabled teleop. How do I know that? I know that because, first of all, this is running. This is running as far as a loop. If we put a probe here, we can see we're in, because I've changed the I pushed the buttons and it changed. So let's see.
But when you release the buttons, it should have gone back to wait.
No. What happened is it disabled it up here because that controlled this. And this button only works. Now this is a gotcha for state machines and periodic task, is that if I'm relying on some signal to carry me through the cycle, that's an actuator, that's not going to be enabled until I enable my teleop. So that's something you need to be aware of. And I've been bit more than once by exactly this situation. So how do I reset it? I reset it by starting and stopping and vice versa.
Could you repeat what you just said about what bit you?
The way, because I was pushing the buttons, I enabled this to run. In other words, this started running in init, and it sat there and waited for me to push the button, and it's not going to do anything until the in fact, we can look at it until the gyro does something. All right, so now I got 90 and it went back to wait. Right, had I turned it on, it would have had a signal going to the motors, and the motors would have started running as soon as I turned the macro on. Right? Does that make sense?
Yeah, that makes sense.
And so I don't have enough guard banding or safeguarding. I probably need to put some other gate here that doesn't start this or doesn't allow those buttons to do anything until this is true. So anyway, that's the thing to watch out for, because it has bit me before. But now we're back in the wait mode. I'm ready to go to teleop, enable. Nothing's running. Now, yeah, now see, in what I just described, it's going to bite me again if I push buttons A or B first. So I need to push my enable button first. And now I can push A or B. I'm in left turn. And so it's got signal on it, and everything's going backwards. So they're indicating they're going backwards. They're just not going very fast. All right, oh yeah, because one is inverted. Okay, what I've just learned is that I have my control signals set too low. So let's go through this again. I'm pretty sure. Now, something else I just violated is I started trying to run a program before I did my check. So let's come back and try this again. So Jim, follow your own rules. And what that means is I want to go back to getting started. Because I have had things sitting on top of this robot and I could have accidentally done something. And so my rule is to use the examples to check every channel before I use the program code. And I didn't do it. So give me a second and we'll try it out. Okay, should be 0 and 6. Okay, so this is checking PWM channel 0. It says failed to connect. Okay, great. Usually that means we already have code running. So let's.
Are you being sarcastic when you say great?
Yeah. nothing like trying to show off and fall on your face. Here we go. All right, now it should have responsive. Yeah, see, I interrupted the code, and so it wasn't receptive to me talking to it with another project. And so that's what I just rebooted or restarted the code that was in the flash, and we get our communications link back. And that's, again, I think one of the advantages of working alongside somebody that's done this is pay attention to their debug scheme and procedures, because it will happen to you. Not that I wish it on anybody, but invariably it's going to happen when there's the most noise and the most time for being frazzled. Okay. Well, 0.3 works, 0.2 works here, so I don't know why it didn't work on mine. Let's verify I got the channels going straight.
So how do you know it's working?
I could hear it. I'm sitting beside it.
Oh, okay.
Yeah, that's, again, I'm big on not having your eyes on it whenever you're trying to do this kind of stuff. Because there's always, especially when you're laying cable around and you got things sitting around it, there's always a chance for messing it up. Okay, so at this point is I'm happy with this. I'm going to reboot this. I'm going to go back and look at, make sure my channels are set up correctly. Yeah, they were all responding though, so something thought it was good. Yep, got 6 and 0. So the other thing is, let's go ahead and change that just because I can. But I can use my joystick while I'm at it. So if we're in left turn, watch the thing take off like a bat. Let's leave this one there. Okay, it says here I've got it under control. Let's go back to robot main. Go ahead and restart code so I have good communications. Talk to me. Oh, I think I still have my example set up. It's trying. Okay, while we're waiting for this, anybody got any questions or questions about how to do a state machine? That's why it's worth practicing several small ones, especially in the blank VI. but it's a huge time saver, especially if you have multiple chores going on in the background that you don't want the driver to have to deal with. Okay. Teleop works. Periodic task works. And let's see. Why is that not showing up? Oh, it's on the inside. Okay, let's try this. It's going at half speed, so I don't know what that means, but it's working, and it's waiting for a signal from the gyro. Now, everybody understand that right now in my state machine, I should be in the left-hand turn mode, because I think I pushed button A. The left-hand turn is what we're getting until it goes to 90 degrees or 89 degrees. So it's stopped. It's back in wait. If I push B, now it goes. Why is, oh, because I didn't change the level of drive. All right. So I'm in right turn in the state machine, but it's still not making anything happen. Okay, so my assessment is I probably have the wrong motor controller specified in my begin statement. So let's kind of go back and see. Nope, says spark. So for some reason, my motor control signal is off by 50% when it comes to my state machine. So that's something I'd have to play with and understand why. Any questions? Anybody get anything out of this?
I got a tremendous amount out of it.
The main thing that I want to reinforce is how valuable robot global data is, how valuable relatively simple tasks are, and how useful it is to take things one step at a time. I think that's all I got. So I guess that's all the information I have. You guys are welcome to, Charles sent me a file that he zipped up for a project, and it worked out fine. I was able to reproduce it at my end. By doing it the way in the PDF that I sent you, you can send me your whole project as you're playing with this, and we can help debug remotely without having to necessarily talk to each other. So feel free to bounce suggestions off of me or request, kind of look over your code if that would be useful. And good luck to everybody in the new season, whatever that may be.
Okay, Jim, I want to thank you. I cannot thank you enough. This has been so very, very valuable for me. Some of my students have had trouble following, but that's just because they don't understand, things like what is a servo and what is autonomous.
Right.
the fact that everything is recorded is great. So I'm going to archive these recordings, and then I'll work with my students to bring them up to speed, and then have them go back and watch the recordings again, and it'll make more sense the second time.
Sure. So I don't even know who we have left.
Just me and Charles.
No, I think Steven, oh, they had to leave, yeah. Yeah, so
Yeah, but just
Mike.
just like about 2 minutes ago.
Yeah. Okay.
Yeah.
Well, it's good talking to you guys. Good luck. And it's been, I mean, it's really neat. As quick as you guys are keeping up with this stuff, it's neat to cover some topics that I don't usually get into with beginner students. So it's nice to have an audience that appreciates what's going on here. So have a good season.
I definitely appreciate it.
All right.
Okay, so long.
So long. Thank you, Charles.